Hello everyone, I am Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course operating system. In this lecture, let us understand how can we detect the deadlock. Up to our last lecture, we have learned two ways of handling deadlock. One way is preventing our system from entering into the deadlock, and the other way is avoiding our system to entering into the deadlock. And this is the third way. What is this third way is in this one we will allow the system to enter into the deadlock if it is like we don't want our system to be in deadlock, but if no chance is there, we will allow our system to enter into the deadlock. But uh, after, like, we will allocate the resources that are requested by the process. After that, we will have an algorithm which helps us in finding, like, after the resources request has been satisfied, whether the system is in deadlock or not. Now, if the system is detected like it is not in the deadlock, then it is called as a safe state. But if the system is detected like it is in a deadlock state, then it is called as an unsafe state. Okay, now if the system is detected as an unsafe state, like deadlock has been detected, then we have to go through the recovery approaches. Deadlock recovery approaches need to be done. Now, how can we do the deadlock recovery? That we will see in our next videos. In today's video, we will be understanding how can we detect our system is in deadlock or not. Right. So to perform this detection approach, we have two approaches here. We need to consider the number of resources, the number of instances of resources we are considering. That means if you consider a printer, if you are having a single printer or more than one printer connected to your system. So depending upon the resources, we are going to consider the type of approach to be followed to perform whether the system is in deadlock or not. So the approach is like this. If you have the resources, single instance resources, if your resource is of single instance, then we need to use wait for graph approach to detect the system whether it is in deadlock or not. If your resources is of multiple instances, then we need to use Banker's algorithm to detect whether your system is in deadlock or not. In this video, we will be understanding in detail about the single instance approach, which where we are going to use this wait for graph algorithm, which helps us in finding whether the system is in deadlock or not. So keep waiting all of you. This video is totally about how can this wait for graph can be drawn, and how after drawing this wait for graph, how can we find out the system is in deadlock or not. Now, what happens in this approach is, in this first approach, where we are considering all our resources are of single instance, right? Now, whatever requests are there, whatever processes are there, whatever um, uh, request and allocation is there, that everything should be represented in the resource allocation graph. You all are aware, in our old videos we have understood, like the processes are represented with the circle and the resources are represented with the square. Do you remember this one? We have done this one. Now if there is an arrow between P to R, then it is nothing but P is requesting R, isn't it or not? Now, if a process, there is an arrow mark between P and R, that means PR resource is under the control of this process. You all are aware of this one. This resource is, this edge is called as request edge. This edge is called as allocation edge. Okay, assigned edge also we can say. Now, having this in the mind, depending upon the request and allocation, we need to consider a resource allocation graph first. Now, by using that resource allocation graph, we are going to draw this wait for graph. So, for our understanding, let us take one small example of resource allocation graph. Let us consider we have five processes. Okay, you can see this where I have considered five processes. You all can see here P1, P2, P3, P4 and P5. Five processes are there, and we have R1, R2, R3, R4, R5 resources are there. Resources are represented with square and processes are represented with circle. I hope you all could able to see. Okay, now If there is an edge between pointing towards from resource to a process, then it is nothing but that resource is under the control of this process. Now, if there is an edge between pointing towards process to resource, then it is nothing but P2 is requesting resource R3. So this is the graph. We all know how to draw this resource allocation graph. Now, once the resource allocation graph is available, from this graph, we need to draw. Let me write down this one. This is called as a resource allocation graph. Resource allocation graph. Now, from this resource allocation graph, we need to draw the wait for graph. How to draw this wait for graph is remove the resources. In the wait for graph, we will be having only processes. Okay, so what are all the processes you have? Just represent those processes. And once the processes are represented, draw the edges between them. I'll just do that one. What we can do, let us consider how many processes we have. We have process P1. So this is P1. We have process P2. Let us draw process P2 here. Okay. Only processes we need to consider. Process P3 and we have process P4. Just we need to represent the processes only, and finally we have process P5. Now we need to draw the edge between processes. If let us consider one example from P1 to P2, there should be an edge. Why? Because P1 is requesting an edge R1 which is under the control of P2. So there is an edge between P1 and P2. So in wait for graph, P1 is waiting for a resource which is under the control of P2. Like that it represents. Got it? Similarly, you can see here P2 is waiting for P5 to release this resource. So we can have an edge between P2 and P5. I hope you all could able to draw these edges. Similarly, P2 is waiting for a resource which is under the control of P3. So that means we need to draw an edge between these two. Similarly, P3 is waiting for an edge which is under the control of P4. So we need to have an edge like this also. And P2 is also waiting for resource has R6 which is under the, this is R6 or 3 which is under the control of this one. Okay. So we need to draw an edge like this. Similarly, P4 is also waiting for P1 to release this one. So there is an edge between like this. So this kind of graph, once the resources are removed and edges are formed between the process, this graph is called as a wait for graph. Okay, this graph is called as a wait for graph. Now once this wait for graph is drawn, what we need to do? Check for any cycle has been formed in this graph or not. You can see here a cycle has been formed. How the cycle has been formed? You can see here the cycle has been formed from this direction like this, and it is coming here and it is going here. So there is a cycle. Did you see? There is a cycle. So if there is a cycle, then what are all the processes involved in that cycle are creating a deadlock. So in our example, what are all the processes? P1, P2, P3 and P4 are creating a cycle. That means these processes are are in deadlock. These processes are in deadlock. But if you see P5, it is not in that cycle. So it is not in deadlock. So only some processes will be in deadlock, some processes may not be in deadlock. That case may also arise. So for this example, whatever we have considered for resource allocation graph, we have designed this wait for graph, and in this wait for graph we need to check for any cycle if it has occurred. Okay, once the cycle has been observed, now for while forming that cycle we need to check what are all the processes that are involved in forming that cycle. Those processes are in deadlock, and here P5 is not in the deadlock. So like this, If there is a cycle, there is a deadlock, that means we could able to detect the deadlock. Now, once the deadlock has been detected, then we need to go for the recovery approaches that we will see in the future classes. But this video is totally about if there is a single instance, then how can we detect our system is in a deadlock. I hope you all are clear with this simple approach. Let us all meet in the next lecture. In the next lecture, we will be seeing about multiple instances if there exist, then how this banker's algorithm help us in detecting the deadlock. Let us all meet in the next lecture. Until then, thank you all of you.